Hello and welcome. Have you ever looked at a sophisticated robot and just wondered, what does it really take to build something like that? Well, today we're pulling back the curtain and demystifying the entire world of robotics engineering. Let's jump right in. This quote just hits the nail on the head. We've moved way past the old idea of a robot arm just doing one repetitive task on an assembly line. Modern robotics, the really exciting stuff, is about creating systems that can actually perceive their environment, make smart decisions, and adapt on the fly. We're talking about a Mars rover navigating a landscape all by itself. That's the kind of evolution we're diving into. So, who are the architects behind these incredible machines? Let's get to the heart of it and define exactly what a robotics engineer is. Honestly, a robotics engineer is a true jack of all trades, and maybe a master of them too. They have to be part mechanical engineer, thinking about gears and motors, part electronics wizard, wiring up sensors and controllers, and part coding genius, writing the software that acts as the robot's brain. It's this amazing fusion of different disciplines that makes the role so incredibly challenging, but also so rewarding. And you can find their work pretty much everywhere you look. I mean, from the factories that build our cars to the operating rooms where robots are assisting in life-saving surgeries. They're in our warehouses, our skies with drones, exploring other planets, even checking on our farms. This field is making a huge impact across almost every industry, and believe me, it's just getting started. Okay, so how do they actually bring these machines to life? The key idea here is what we can call intelligent motion. This isn't just movement, it's movement with a purpose. Let's take a look at the blueprint engineers use to make this happen. Just look at the sheer range of responsibilities here. It's kind of mind-blowing. 1 minute, an engineer could be designing a physical joint or a motor mount. The very next, they're buried deep in code, figuring out a complex algorithm for avoiding obstacles. This is the real challenge of the job. They have to fluently connect the physical world of atoms with a digital world of bits. So with all these different pieces in play, you've got hardware, you've got software, you've got sensors, it begs a really important question. How in the world is a robot system actually put together so it all works in harmony? It's all about building in layers, kind of like a stack. You can see how it flows here. Right at the bottom, you have the physical stuff, the metal, the motors, the chassis. The layer just above that is the interface that lets the code talk to the hardware. Then you get to control, which handles the raw commands like spin this wheel. On top of that is planning, which figures out the bigger picture, like the best path to get across the room. And feeding into that is perception, the robot's senses, which tells the very top application layer what's going on, so it can make the big decisions. See how each layer relies on the one below it? It's a really elegant structure. Now, to build that entire stack from bottom to top, an engineer needs a pretty powerful toolkit of knowledge. So let's open up that toolkit and see what's inside. Okay, the absolute foundation is something called kinematics, which is really just the math of how things move. Forward kinematics is pretty straightforward. You ask, if my robot's joints are at these specific angles, where is its hand in space? But inverse kinematics, that's where the real magic happens. It flips the question. To get my robot's hand to that exact spot, what angles do all my joints need to be? This is totally essential for any robot arm or walking robot. So once the robot knows how to move its limbs, it needs to figure out where to go. For that, you have algorithms like A-star over on the left. It's great for finding the shortest, most efficient path on a map you already know, kind of like your phone's GPS. But what if the space is really cluttered and complex, like a messy workshop? That's where something like RRT star on the right shines. It sort of explores the space randomly, but smartly, finding a workable path even when the environment is a total mess. But of course, all this brilliant planning is useless if the robot is basically flying blind, right? So how does a robot actually see and understand the world around it? Well, it uses a whole suite of different sensors. Cameras are its eyes for spotting objects. LiDAR shoots out lasers to build incredibly detailed 3D maps. And IMU is like its inner ear, giving it a sense of balance and orientation. And often, these sensors work together in a process that is just amazing. It's called SLAM. That stands for Simultaneous Localization and Mapping. It means the robot can do two things at once. Build a map of a place it's never been before, while at the same time figuring out its own exact position inside that map it's currently building. Wild, right? So we've got the hardware, we have the math for motion,
we have the sensors for perception. How do you get all these different complex pieces to talk to each other? For a huge part of the robotics world, the answer is ROS, which stands for the Robot Operating System. Now, ROS isn't an operating system like Windows or Mac OS. It's better to think of it as a universal translator and a giant switchboard for your robot. Every part, like your camera sensor, runs as its own little program called a node. These nodes then publish their data onto topics, which are like public radio channels. Another node, maybe the one doing obstacle avoidance, can just tune in to the camera's channel to get the data it needs. It's an incredibly flexible way to build things, and it even comes with powerful simulators like Gazebo, so you can test your robot in a virtual world before building a single physical part.
And the ecosystem around ROS is just massive. You can code in super fast C++ or easy-to-use Python. You can run it on cheap hardware like a Raspberry Pi or on a supercomputer like an NVIDIA Jetson. And you get amazing tools like MoveIt for motion planning. The whole community is now shifting to ROS 2, which is even more robust for serious industrial-grade robots that need to be reliable every single second.
All right, so let's say all of this sounds awesome, and you're thinking, I want to do that. How do you actually turn that passion into a career? Let's chart out what that journey typically looks like.
A lot of people start out as an intern or a junior engineer, maybe focusing on one specific piece of the puzzle, like writing the code for a single sensor. As you get more experience, you move up to a senior level where you're responsible for bigger systems. From there, you might become a robotics architect, the person who designs the entire system from the ground up, or a lead who guides whole teams in solving the next big challenges in the field.
So what does it take to really crush it in this field? Well, theory is important, but you have to build things. You have to get your hands dirty. Go really deep on the fundamentals, like kinematics and control systems. And, for sure, master the tools of the trade, like ROS. But maybe most importantly, you have to learn to blend hardware and software thinking. The best robotics engineers are fluent in both languages.
And that really brings us full circle, back to where we started. Being a robotics engineer, it's about so much more than just sitting and writing code. It's about taking metal, circuits, and silicon, and orchestrating them into a machine that moves with purpose, with intelligence. You are, quite literally, a creator of intelligent motion.
So as we finish up here, I'll just leave you with this one thought. You've now seen the blueprint, you've seen the toolkit, and you've seen the career path. The only question left is, what intelligent motion will you create? Thanks so much for joining me for this explainer.